Hello everybody, and welcome back to the final class of Math 105. Plan for today is we're going to finish Standard 20, talk about a different type of quadrilateral from last time, and kind of tie everything back together. I've got my usual office hours today, assuming you're watching this on Wednesday, from 10 to 10:50 and 2 to 2:50, and Thursday, from 10 to 11 in the morning, 1:30 to 2:30 in the afternoon. And this time, I want you to know that the Standard 20 quiz, hopefully by the time you're watching this, has been posted, and the Standard 20 quiz will be due Friday evening. As well, also due on Friday, will be Exam 4, Standards 1 through 20. Dr. Gerstel, why aren't you giving us more time on Exam 4? Why are you making it do the same time as Quiz 20? The reason is because I want to make sure I have enough time to grade the exams. So I'm making them due Friday, because if I made them due like Monday or something, I just wouldn't have time to grade Exam 4 before you need to start doing the final exam for this class. So, something to keep in mind. Sorry it had to work out that way, but under a little bit of a time crunch. Here. So, what do you call it when you have so much trash, you lay it all out on the ground, and it's 3 feet long? You have so much trash, it's like 3 feet of it. What do you call that? You call it a junkyard. Okay, so you may recall from Monday's class, we said that a Sakhiri quadrilateral is a quadrilateral, something made up of 4 lines like this, A, B, C, D, where the 2 angles at the base of the quadrilateral are both right angles. So angle A and angle B are right angles. And the 2 sides of the quadrilateral, AC and BD, are equal in length. And what we proved in Monday's video has to be true is that the summit angles will have to be equal to each other. And as long as you have side angle, side, 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 side. So in Euclidean geometry, in the Poincare disk, in spherical geometry, all of those are models of geometry in which the 2 summit angles will have to be equal in any Sakhiri quadrilateral. But we also showed in the last video that while the 2 summit angles have to be equal, they don't necessarily have to be right angles in non-Euclidean geometry. While in Euclidean geometry, these 2 angles at the top will have to be right angles. In the Poincare disk, they turned out to both be acute angles, whereas in spherical geometry, they both turned out to be obtuse angles instead. And now, I'm going to look at a different type of quadrilateral, this one named after a French mathematician, Lambert, and talk about how are Lambert quadrilaterals different in Euclidean versus spherical versus Poincare disk models of geometry. So Lambert quadrilateral is pretty easy to define. It's just going to be a quadrilateral that has at least 3 right angles in it. So a Lambert quadrilateral is one with at least 3 right angles. So here's an example. A, B, C, D. Say angle A is right, angle B is right, angle C is right. That's enough to have a Lambert quadrilateral. So you might be asking, looking at this, if angle A at A is a right angle at B is a right angle, and angle at C is a right angle, does that necessarily mean that the angle at D also has to be a right angle? In order for something to be Lambert, it has to have at least 3 right angles, but it could be the case that all 4 angles are right angles as well. That would, something like a rectangle, for instance, or a rhombus, would also, not a rhombus, strike that from the record. Something like a rectangle or a square would definitely be considered Lambert as well, even though all their angles are right. So in this picture, it certainly looks like angle D would have to be a right angle as well. But does that have to necessarily be the case, do you think? Well, let's take a look and see at how do Lambert quadrilaterals differ from in Euclidean versus hyperbolic versus in elliptic geometry. So to start out, let's see if we can draw ourselves a Lambert quadrilateral with at least three right angles in spherical geometry. So draw a sphere, and we need a quadrilateral with at least three right angles. I'm going to make one of my sides the equator because it's so nice to have. We'll have this point be A. We'll have this point be, we'll have this point be B. We'll have these longitude lines coming from the North Pole down through A and B, so these are going to be right angles. Dr. Gersel, you're getting sloppy with your things here. So we have two right angles already. I want to draw another line in a way that makes another right angle at C here. Let's see what happens if we continue this line onwards to make a fourth angle at a new point D. This is hard to draw by hand. So we end up with a quadrilateral that looks something like this. Let's try it just one more time. There we go. That's a little better. So we have a right angle at A, a right angle at B, and a right angle at C. So we could say here that the quadrilateral ABCD is Lambert, because we have three right angles at A, B, and C. But how about this angle at D? Is this a right angle? Doesn't look like a right angle to me. In fact, this Lambert quadrilateral in spherical geometry is obtuse. Turns out it's not the case that in spherical geometry, Lambert quadrilaterals have to, if you have at least three right angles, you have to also have a fourth. In spherical geometry, anytime you have a Lambert quadrilateral, meaning one with three right angles in it at least, the fourth angle is not going to be right, it's going to be an obtuse angle, which will make it different from Euclidean geometry, where the fourth angle will also have to be right. Let's compare that to the Poincaré discipline. So here, I'm going to draw a couple diameters, one going straight up and down, one going from straight left to right. So it looks like a crosshairs here. And where they intersect in the middle is going to be my point A. I'm going to draw another arc that does something a little bit like this. And then this point will be our point B. And finally, notice that at A and B so far we have right angles. And finally, let's draw another arc here. And then this point, we'll have another point C. So at A, B, and C, I've drawn all of these lines so that they all match up at right angles. So at A we have a right angle, at B we have a right angle, at C we have a right angle. And this will be our fourth angle at our fourth vertex of the quadrilateral at point D. So at A we have a right angle, B we have a right angle, C we have a right angle. What can we say about this angle here at D? That's not a right angle, that's an acute angle. So here we have that our quadrilateral ABCD is Lambert. still, but angle D this time, it's not obtuse or a right angle, it's an acute angle. Obtuse with spherical and acute with Poincare disk. Why does that sound familiar? That's related to the summit angles in a Sakhiri quadrilateral. In Euclidean geometry, we said the summit angles of a Sakhiri quadrilateral have to be right angles, just like the fourth angle in a Lambert quadrilateral. In spherical geometry, we said the summit angles are going to be obtuse, just like the fourth angle in a Lambert quadrilateral. And finally, in the Poincare disk model, when we looked at Sakhiri quadrilaterals, the summit angles were both acute, just like the fourth angle in an Lambert quadrilateral. Somehow there's this sort of association here with when making quadrilaterals with Poincare disk, acute. Elliptic geometry, obtuse. Euclidean geometry, right angles. And if you remember, that sort of sounds similar to what we said about triangle angle sums in each of these three models. Triangle angle sums in Euclidean geometry, 180 degrees exactly. Spherical geometry, greater than 180 degrees. The three angles had to sum to greater than two right angles. Whereas in the Poincare disk, triangle angle sums all came out to less than 180 degrees. Angles all came to less than 180 degrees sum. So there is some sort of relationship here between the angles in a Poincare disk of the triangle or quadrilateral tend to be smaller than the angles in a triangle slash quadrilateral in Euclidean geometry, which are in turn going to end up being smaller overall than the angles in a triangle or quadrilateral in spherical geometry. So let's write some of this down. We can actually state some of this as propositions a little bit more formally. So first of all, I'm going to state a proposition about Euclidean geometry, Sakhiri versus Lambert quadrilaterals. Treat this as a proposition. And what this proposition says is that in Euclidean geometry, every quadrilateral that is Sakhiri or Lambert must be a rectangle. In other words, for Sakhiri, what this means is that if the two base angles are right angles, and if AC is equal to BD, so this is a sort of a subheading of what does this proposition say for Sakhiri. What this means is that if the angle at A and the angle at B are right angles, and if AC is equal to BD in length, these two sides have the same length, and if at A and B we have right angles, then the other two angles will have to be right angles, and the angle at C and the angle at D will also be right, and we'll also have AB is equal to CD in length. The summit and the base will have the same length. AD and AC don't have to be the same length. The sides could be a different length than the base and summit, We don't necessarily have to have a square, in other words, but the top and bottom will be the same length, and all four angles will have to be right angles. To me, this actually feels sort of like side angle side in a sort of way, in that it says if you have two triangles that are equal in some ways, they'll have to be equal in every way. If no two triangles are equal in three pieces of information, then they'll have to be equal in every other piece of information as well. In this case, if we have this shape, which is like a Sakhiri quadrilateral in Euclidean geometry, where you have some properties of a rectangle, namely two of the angles are right angles and two of the sides are the same length, then everything else has to also be the same as a rectangle, and that the top and bottom will have to be the same, and the last two angles will also have to be right angles. If you have some properties, if you have enough properties of a rectangle, you'll automatically have to have all the others in Euclidean geometry. Or in a Poincare disk or spherical geometry, this proposition doesn't work, because you can have quadrilaterals that are, say, Sakhiri, but aren't rectangles, where the last angles are not right angles, or the other two sides are not the same length. But in Euclidean geometry, having some properties of a rectangle from being Sakhiri will give you the other ones for free. And we could similarly say something about Lambert quadrilaterals in Euclidean geometry. Basically saying, in Euclidean geometry, this will be A, this will be B, this will be C, this will be D, phi, phi, fiddle, he, he. We could say that if angles A, B, and C are all right angles, what this proposition is then saying is that then angle D must also be right, AC will have to be equal to BD in length, and AB will have to be equal to CD in length. Meaning, if you're looking at a quadrilateral where you have two right angles, like so, or three right angles, then the last angle will automatically have to be a right angle, and the two sides will have to be the same length, and the top and bottom, the base and the summit, will also have to have the same length. If you have enough properties of a rectangle, meaning you have at least three right angles, then you'll automatically get everything else a rectangle has for free. You have to have that fourth right angle, you have to have the two sides of the same length, you have to have the base and summit are also the same length. This proposition is like side equal side, 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 side in that way. It's saying if you have enough properties in common with a rectangle, you'll have to have the rest in common as well. Proposition again, not true for Lambert quadrilaterals and say the Poincare disk model, because here we have three right angles, but this is not a rectangle. The sides do not all, AC and BD, for instance, do not have the same length. And the last angle is certainly not a right angle. This is only a proposition that holds true in Euclidean geometry, not in the other two models that we see. So one last proposition to round out this video / the semester. And that's going to be a proposition kind of summing up what we said in a theorem. A theorem is the same as a proposition here, just kind of fancier because it has a fancy name to it. And that's going to be Sakhiri's theorem. And what Sakhiri's theorem says is that the angle type of the summit angles in any Sakhiri quadrilateral in any Sakhiri quadrilateral, slash the fourth angle in any Lambert quadrilateral, all of these are going to be, first of all, right angles if you're looking at Sakhiri quadrilateral or Lambert quadrilaterals in Euclidean geometry. The summit angles and fourth angle, and the summit angles in Sakhiri and fourth angle on Lambert are going to be obtuse angles if you're looking at any model of elliptic geometry. And finally, the last angles are going to be acute angles if you're looking at any model of hyperbolic geometry. So in other words, that's pretty much summing up what we saw throughout the last couple of videos. That anytime we're looking at a Sakhiri quadrilateral, you have the two base angles or right angles. The summit angles are going to be right angles in Euclidean, obtuse angles in elliptic, and acute angles in hyperbolic geometry. And similarly, if you're looking at a Lambert quadrilateral, where you have a quadrilateral with three right angles to start with, the fourth angle will also be a right angle in Euclidean geometry, will have to be an obtuse angle in elliptic geometry, and an acute angle in any model of hyperbolic geometry. Remember, elliptic geometry is kind of an umbrella of all geometry satisfying the elliptic parallel postulate, including spherical geometry. And hyperbolic geometry is kind of an umbrella of all these models of geometry that happen to satisfy the hyperbolic parallel postulate, including the Poincare disk model. All right, that's going to end the semester, I think. Really enjoyed teaching this class despite all the trials and tribulations this semester has brought. It's my first time teaching this class. I hope to improve upon it in the future. But you've all been a great group to work with. Yeah, thank you so much for making this a good semester for me. Hope you're all still staying okay and healthy and such. This has been fun times. And I hope you all have a good winter break and good final exam season. Even if some asshole professors are giving you midterms the week before finals. Okay, hope you're all doing okay. Take it easy. Peace out.